in this session, we want to talk about implementing some monitoring and debugging features in P4. And unlike the morning sessions, the afternoon sessions are going to be less talking from us and more programming from your side. So I'm just going to introduce the setup that we're going to work with and the exercises that we want to do in this session. And then we'll start programming, and then we'll be around for questions. So let's get started. This is the setup that we want to work with during this session. We have a network of 3 switches. S1 is connected to 2 hosts, H1 and H11. S2 is connected to 2 hosts, H2 and H22, and S3 is connected to H3. But we don't care about S3 and H3 in this session. So now let's suppose that, and also suppose that all of these switches are running the basic.p4 program that we work with during the morning sessions. So each one of these switches is just doing the regular destination-based IP forwarding. Well, now let's say that H1 starts to send some traffic to H2, and this traffic is low rate, and all the switches and links in the network can handle that. So the traffic can just be processed and forwarded fine, and yeah, everything is going to be just fine. But if after a while, H11 decides to send some traffic to H2 at a very high rate, such that the link between S1 and S2 cannot accommodate both flows, then we're going to end up having congestion. So basically, packets of both flows are going to be queued up at S1, waiting to be sent to S2. And once the queues fill up, the packets are going to start getting dropped. Well, the network congestion is not a new problem. It has been studied since the beginning of internet. And typically, what you want to do in this kind of situation is for the end host to detect that congestion has happened and basically slow down so that they can share this bottleneck link more effectively. And there are multiple ways for the end host to detect congestion. They can look at the RTT of the packets. If they start to increase significantly, they can suspect that packets are getting queued up somewhere along the path. They can look at packet drops or duplicate acts, etc. And all of this is good. You know, there are a lot of congestion control algorithms just relying on the end host and these indicators. But given that the congestion is actually happening in the switches inside the network, the switches are in a great position to actually detect that congestion is about to happen and then send notifications to the host so that they can slow down before anything bad happens in the network. And this is called explicit congestion notification. And all the exercises, the 2 exercises that we're going to do in this session are basically ways to implement explicit congestion notification. The first exercise is basically going to, in the first exercise, we're going to implement the common approach for explicit congestion notification, which is setting ECM bits inside the IPv4 header, which all the regular switches these days can do that. And then the second exercise, we're going to look at a fancier way of implementing explicit congestion notification, which you cannot do with switches today, but programmable data planes and P4 enable that. So with that, let's look at our first exercise. In the first exercise, we want to implement explicit congestion notification by setting up some bits inside the IPv4 header. Here's a picture of the IPv4 header. Inside the header, we have 8 bits that we call type of service bits, or TOS, that are marked as yellow on the slide. And the first 6 bits of these 8 bits are actually used for differentiated service that we're not going to work with in this exercise. But the last 2 bits are called ECM bits, or explicit congestion notification bits. And these bits can be used for communicating congestion notification between the host and the switch. How does that work? If the end host doesn't want to receive any congestion notification from the network or can't process those kind of notifications, it will just set those 2 bits inside the header of the packets that is sending out to 0. So if the switches see packets that have these 2 bits set to 0, they know that they shouldn't do anything about it. Just forward the packet regularly. But if the host actually wants to receive some notification from the network about congestion, it can set either of these 2 bits to 1 to just notify the switch that, yes, I want to receive some notifications and I'm capable of processing them. So when the switch receives a packet from a host that actually wants to receive this kind of notifications, it can look at different statistics. For example, let's say the queue depth at the time that the packet arrives at the switch. And if it's beyond the threshold, it can assume that congestion is about to happen and then set both bits of the ECN in the IPv4 header to 1. And then send this packet out. This packet gets to the receiver copies the bits on the reply packet, so the notification is going to get to the end host. So this is exactly what we want to do in the first exercise. We want to implement this in P4. So let's go over how we can do that. Here is a picture of the switch architecture for V1 model that Stefan told you about in the morning. So basically, when a packet comes in, it is processed by the ingress pipeline, as you also saw in the basic.p4 program. The ingress pipeline sets the egress spec, and then gets the package to the traffic manager. Inside the traffic manager, the packets are going to be queued up based on that egress spec that was set in the ingress pipeline. And then once the packets get out of those queues and they go to the egress pipeline, then they can be processed, you can do some more processing on them and then send them out. So in the V1 model, the queue depth that the packet experiences when it enters the traffic manager is measured, and then it's made available to the programmers in the egress pipeline. So basically, you can actually see what was the queue depth for the packet inside the traffic manager inside the egress pipeline. So what we want to do is that we want to augment that basic.p4 program that you worked with in the morning to basically add some logic to the egress pipeline to actually do the kind of ECM processing that I just described. So let's take a coding break and actually do that. So if you go to your VMs, let's see. Wait. OK, this is not working. Anyway, let's wait for this to load. Anyway, if you go to your, inside your VMs, you go to the exercises folder. There's a folder called ECN that has the starter code for this exercise, and also a README file that is going to guide you through step by step. It doesn't work. Yeah. That is going to guide you step by step through how to actually add that logic into your program. So if you look at the starter code, I really want to show you here, but this is completely gone. It doesn't do anything. So if you actually open that starter code, there are multiple things, there are multiple to-dos that are marked in the starter code that you have to implement. So the code itself is the basic.p4 program that you saw in the morning. So the headers that are defined are the Ethernet header and the IP header. One change that you have to do in that program is that inside the IPv4 header that is defined there, we're looking at all the 8 bits of type of service as one field, but because you want to look at the ECM bits, you have to actually partition that field into 2 fields so that you can actually parse the ECM bits and actually work with them in the pipeline. So that's one change that you have to make. The parser, I believe, is unchanged because you want to parse Ethernet and IPv4. And the ingress pipeline is also unchanged because you just want to do the destination-based IP forwarding and see where the packet should go. Then egress pipeline is where you have to add your logic, which is you actually want to use the standard metadata, but basically the queue depths from the standard metadata. You actually want to first check the packet to see if the host wants to receive any ECM bits or not, ECM notifications or not. And if it wanted to, you can check the queue depth. And if it was beyond the threshold, you can set the ECM bits. So, yeah. No, I know, but it's completely gone. Yeah. Doesn't even, go back to the slide. So, yeah. So, so let's get started. Me and the TAs are all going to be around, so just let us know if you have any questions. We are going to stop this exercise in about 25 minutes and go through the solution if you want, and then start with the second exercise. All right. Let's see how far we made progress. By show of hands, how many people actually made significant progress? Great. How many people completely solved it and saw congestion? Good. So let's actually go through the solution very fast. This is ECN. The change here, the only change that we needed to make here inside the definition of the IPv4 header was to basically partition the previously type of service field into 2 different fields, the first 6 bits as deepserve and the next 2 bits as ECN. Then let's go to the egress pipeline. There we go. So here we're just checking using an if statement that if the ECN, those 2 bits of ECN are either 1 or 2, meaning that either of the 2 bits are set, then we want to use the queue depth that we can get from the standard metadata and basically compare that with the threshold. If that was more than the threshold, then we do mark ECN, which is basically just setting those ECN bits to 1, which is going to make the field value 3. Any questions? The second part of the exercise, the second exercise actually. So one problem with ECN is that it can only show us that there's congestion somewhere in the network, but it doesn't show us where, and it also doesn't show us the extent of the congestion. So it would be great if we had some way for each switch to put something like a statistic record, if you may, on the packet to tell us exactly what happened to the packet when it went through that switch. So for example, it would be great if, as the packet was going from H1 to H2, let's say when it was at S1, S1 could put something on a packet that says, well, the packet was at switch S1, and here is the queue depth that the packet experienced. Or any other statistics that the program is interested in, but for the sake of our exercise, we're just using queue depth. And then when the packet moves to S2, this S2 can add another header, some statistic record of its own to say that the packet was here, this is the queue depth that it experienced, and then send it to the end host. So when the end host receives the packet, it has a full picture of what happened to the packet in the network. So you can actually see which was the switch that actually was congested, and how big was the queue, how bad was the congestion. So we're calling this approach multi-route inspection, or MRI for short, and this is what we want to implement in the second exercise. So, I mean, these headers are custom headers, so you can really define them any way you want, but here we've just decided to use IPv4 options for putting these statistic records. Okay, let's just go through how we've defined these headers in our starter code. So if an end host wants to receive, these statistic records on a packet, it needs to add something to the IPv4 options that we're calling the MRIT header. So basically, we have defined a new option inside a new option type inside the IPv4 option part, which is specific to MRIs, just some code. And if that is true, it means that there's going to be an extra header, MRIT header, inside the IPv4 option. So that's what the host puts on the packet. And this header just has one field count that shows how many switches the packet has passed so far, so how many records we have on a packet so far. And initially, it's going to be set to 0. So if this header is not present actually in the packet, so if you don't have the IPv4 options at all, or we have IPv4 options, but we don't have the MRI header in it, the switch shouldn't do anything. It shouldn't put any extra records on a packet. So just a reminder from the morning, how you could check in the control pipeline that you have a header or not is using these validity functions. So header that is valid or is not valid, or set valid, set invalid. So that would be the MRIT header, and then we actually want to have the statistic records themselves. So for each statistic record is going to be of type switch T, which is going to contain 2 fields, the switch ID and also the queue depth that a packet has experienced. And there's not going to be only one of these. Each switch is going to put its own switch T header on the packet. And the way we're representing that is using a header stack. So header stacks were actually briefly mentioned, I think, in the morning session. But just a brief overview is that header stack is just an array of headers of the same type. And what you can do is that you can define them this way. So it can't have a dynamic size. So you actually have to, when you're specifying them, you actually have to specify what is the maximum size that that stack is going to grow into. And then inside the parser, to actually parse these headers, there is this pointer called next that is pointing to the first free element of the stack. And initially, it's just pointing to the first element. So once you parse one instance of that header into, let's say, stack.next, then this next pointer is going to automatically go forward one and point to the next free element. And you can check, there's another pointer called last that points to the last used element of the stack, and then there's something called last index that actually gives you the index of the last used element in the stack. And so that would be inside the parser. Inside the control block, if you want to refer to the header stacks, you can use regular subscripts like you use arrays, and you can also access the size of the stack. If you .size, you can push a set of new headers to the front of the stack, and you can also pop a set of headers off the top of the stack. And that's going to come in handy because especially the push front one, because each switch is going to push a new stack, a new header into the stack. So to put this all together, all the headers that we might have in a packet is the Ethernet header, and then the IPv4 first 20 bytes, so without the options, and then the IPv4 option header. Then if the MRI option is actually available, then there's going to be an MRIT header, and then there's going to be a stack of switch T headers. So what you want to do is that inside the parser, you actually want to go ahead and parse the Ethernet, parse the IPv4 header, see if there are any options or not, and the way you can check that is by checking the length of the IP header, and then parse the options, check the option type. If the option type was MRI, then you want to go ahead and parse MRIT, and based on that count field, you know how many headers, how many switch T headers are going to be inside the packet. Then you want to kind of recursively go ahead and use that .next pointer to parse all those switch T headers that are inside the packet. There's also another. Are there any questions here? No. And there's also one other new thing that you're going to see in the starter code, which is header verification. So when you're doing parsing, it could be possible that you see a packet that is malformed, or it's in protocol that you don't know how to parse, or some other error. You know, it could be a header that you know, but some of the values of the fields are not correct. So in all those cases, what you can do is to move the parser to the reject state and throw an error. And there are a set of errors that are predefined in P4, like no error at all, or packet too short, no match. Some things similar to that, but it's also possible for the programmers to define their own kind of errors. So for example, let's say that you actually want to check if, when you parse an IPv4 header, you want to then check if the version number inside the header is actually correct or not. So the way you can do that is to basically use that verify statement, and that takes two arguments. The first argument is a Boolean expression that is going to be evaluated on the packet that they've just parsed. And if that expression evaluates to false, then the parser is going to move to the reject state and throw that error that you specify as a second argument. So you're going to see examples of this in the starter code. I think it's checking for the length of the IP header to be correct, but yeah, just a heads up about what it means. So now let's go to the actual coding part, if I can find my terminal. Okay, and just briefly go over the to-dos. Yeah. So the headers that I just talked about are already defined in the starter code, and there's, by the way, a README file again inside this MRI folder that is going to guide you step by step through how to do the exercise. And then you have to define the parser after the IPv4 header all by yourself. And there is going to be, and then again, the ingress pipeline is going to be the same thing that it was as before. You want to do regular destination-based forwarding. And in the egress is, you have to add some extra logic. Basically, if there was an MRIT header inside the packet, you want to increase the count by 1 because you want the switch to add some new header. You want to push the new switch T header inside the header stack. And something very important here is that because you're using IPv4 options to contain all of this information, you need to make adjustment to the length field inside the IPv4 header. So for example, there is the header length that is going to get incremented. There is the option length that is going to get incremented when you add a new header to the stack. And then there's going to be a total length. I don't know why it's not here. But I think it's there in your starter code. Also, there's a total length field inside the IPv4 header, and that also needs to be incremented. I think that, and then in the deparser, you also need to emit the MRIT header and all the IPv4 options, and MRIT header and all the whole header stack of switch traces. So this is kind of more involved than the previous example. Let's get started. And again, we're going to be around if you have any questions. Hopefully, you've made enough progress with the exercise. Let's look at the solution, because we only have 5 minutes to the break. So one of the things that we had to do in the solution was to actually parse the headers. Let's go to the parser. So once we parse the IPv4, in parsing the IPv4 header, we actually look at the length, and if it is 5, it means that we don't have any options, so we go to the accept state. But if it is anything other than that, we go to parse the options, and note that right before this select, we are actually checking that the IP header length is actually greater than 5, so the only two cases is that it's either 5 or greater than 5. So short packets are not going to even go through the rest of the parser. In the option part, IPv4 option parser, we extract the options. We check the option type inside the option, and if it is the MRI option, we go ahead to parse MRI, and in the default case, we just basically accept and go to the pipeline. For parsing the MRI, we just parse it first, and then one important thing here is that that count field inside the MRI T header is actually showing us how many switch T headers we are gonna see inside the packet. So we're gonna keep some metadata inside the parser to kind of keep track of that count. And then if that count is 0, it means that this is kind of the first switch that is seeing the packet, and there's no switch traces in it. So we just go to the accept state and finish the parser and go to the pipeline. But if there was anything other than that, it means that there are a couple of switch T headers inside the packet, so we're going to go ahead and parse them. And the way that works is kind of recursive, as I kind of mentioned in the slides before. We have this .next pointer that you can see here that is kind of pointing us to the first available element inside that header stack. So we parse one switch T header inside the header stack, and we decrement one from the remaining switch traces that we have to parse, and then we check whether we have anything else to parse or not. If we don't, we exit the parser, but if we still have things to run, we go back to the same parser state and keep doing this till we parse all the switch T headers. Any questions? Yeah. Sorry, what's that? Why do we need the keyword next, you were saying?
So this keyword, right, when you say packet extract header SW traces dot next. Right?
This?
So, if you see this, the keyword is not actually is part of the header structure.
Sure, this is just some extra, let's say, property that P4 language provides for you. So it's not part of the header, it's just some pointer that is built into P4 to help you parse this header stack. So think of the whole header stack as one object that has this array and also these kind of pointers to help you work with it.
No, the question here is, why do we need next? Even if we don't give next, isn't it implicit that, we are actually going to pass this type of header next, right?
No, but you want to, so the way extract works is that you want to say that what is the header that you want to parse, and where are you going to put it, right? Right. Even like in the previous examples that you've seen, you give it a header instance to extract and put the information inside, right? So if you just don't have next here and write header.sw traces, it is pointing to a stack of elements, right? A stack of headers. So when you parse, you don't know which element you have to put that information in. So that next is actually pointing to the specific element that you want to parse that information into. Does that make sense?
So this keyword is only for the stack of headers?
Yes, exactly. That's only for the stack of headers, and it's only available inside the parser.
Okay.
Yeah. Any other questions? Okay, great. So now let's move to the egress pipeline. Oh, no, I ran over it. Okay. So here, let's first look at just our control logic. That's pretty simple. If there is an MRIT header inside the packet, it means that we need to add those switch trace headers, and then we apply the switch trace table. And inside that table, we actually want to implement one action that actually adds that header into the packet. So the way that works is that first we want to increment the count inside MRI to basically reflect upon the fact that we're adding one header. Then we want to push one element to the front of the stack. And this is going to be the first element, so we can access it with 0. And then we're going to set the switch ID inside that first element as the switch ID that is given to us as an argument of the action. Yes? Sorry, say that again?
How is the switch ID getting passed in?
It's not getting parsed in. It's an argument to, you're talking about this switch ID, right?
Yes.
Yeah, so it's an argument that is passed into the action. So when the controller is putting rules inside this table, it is going to specify this argument. So basically, the controller is going to put some rules. Let's say for switch 1, it's going to put some rules on this table that says, let's say for all the packets, like for star, the action is add SW trace 1. So basically, that is an input argument into the action. The controller specifies that for every single rule inside the table. Does that answer your question? So that is actually not something that you parse. Let's say you've seen an example of that in the destination, like in basic.p4. So the way that works is that for every, like you have this action. Let's go back to here. Yeah, so here, IPv4 forward. You had this other action that took into argument what is the destination address and what is the port, right? So there's this option for you to actually give some arguments to action. So when you're creating the rules, you can actually specify these arguments, and when that action is being executed, those arguments are passed to the action. That's exactly the same thing that we're doing here. We're passing the switch ID as an argument to this action. Yeah.
I see there is a typecasting on the queue depth. What is
Sure.
the rule for the typecasting?
That is, what do you mean?
Like, why do I have to typecast here instead of other places?
I think the reason is that standard metadata.queueDepth is of a different type. So we defined the switch, the SW_T header ourselves, and we defined some type for it, queueDepth. And then the standard metadata.queueDepth is of a different type, so that's why you have to do the typecast.
But does the compiler automatically adjust the destination bit width to whatever that is defined? Why do you need a typecast? That's what I'm really
I mean, it's from a...
In P416,
Yeah.
if the right-hand side and left-hand side are different bit widths, then you need a cast explicitly. If they're the same width, then you don't need a cast.
Yeah. Any other questions? Are we running out of time? Yeah. Okay. I'll go over the rest of it very quick. So, yeah. So then we pushed another element. We set the switch ID and the queue depth for that specific header. And then here are the changes that we have to make to the length inside the different fields of the IPv4 header. So we basically increment the header length by 2, the option length by 8, and the total length by 8. And the reason these are different is that because kind of the unit that they're counting by is different for header length and total length. That's the only reason. And then inside the deparser, we just want to emit whatever we've parsed, which is the IPv4 option, MRI, and SW traces. I think that's about it.
Just
Yeah.
Over here.
Yeah.
Just a couple of questions on the egress processing. What do we need to implement this action as a table?
Why do we need to implement it as a table?
Can you implement it without using a table, or is it required that we use a table to implement?
That's a very good question. I think you could actually do it because just with one action, like we did for ECN, especially because you're checking whether MRI was valid or not and then applying it, so I don't think there's any reason for that, yeah. Oh, yes, that's right, yeah, the switch ID, yeah. Yeah.
And then we don't specify a table size here, it's by default 1?
Yeah, if you don't specify anything, the compiler will choose something, yeah. Any other questions? Great.
So let's say Mina.